class, we will try to learn a technique how to implement the space vector based PWM based only on sample reference phase amplitude. Okay. So, we will study a simple technique, that is SV PWM, SV PWM using only the sampled reference phase amplitudes. Okay. Let us draw our space vector diagram. So, space vector diagram, you have from a 3-phase system, the periphery is a hexagon. Okay. This is our sector 1. So, this is the hexagonal space vector based structure. This is 1 0 0, this is 1 1 0, 0 1 0, 0 1 1, opposite to this one 0 0 1, opposite to this one, this is 1 0 1. This is our sector 1, S1, S2, S3, S4, S5, S6. In the previous class, we found for any sector, when the Vs, the reference voltage space vector in any sector, and if the angle is measured from the start of the sector, the period T1 with which the start of the vector is switched and the T2, the end vector forming the triangular sector and the 0 vector are switched, can be found out from this equation. T1 is equal to 2 by root 3, this we have derived. Our Vs, mode of Vs divided by VDC, Ts sin pi by 3 minus alpha T1. T2 is equal to 2 by root 3 Vs mod divided by VDC into Ts into sin alpha. See this one, we also know that equation V alpha is equal to 3 by 2 Va and V beta is equal to, from the alpha beta transformation, root 3 by 2 Vb minus Vc. This also we have derived. Now, how we can get this T1, T2 in terms of Va, Vb and Vc? Let us say T1 in sector 1. T1 is equal to 2 by root 3 into, let us take Ts by VDC, these are constants outside, VDC into okay, Vs mod into, we can express Vs into sin pi by 3 minus alpha, we can expand this one as cos alpha sin pi by 3 minus Vs sin alpha cos pi by 3. This is T1. What is Vs cos alpha? We are alpha. Our alpha is in this direction, beta is in this direction. For sector 1, alpha is along the vector for which the T1 period, the start of the vector. So, Vs cos alpha, this is equal to Vs cos alpha. Vs cos alpha is equal to the corresponding V alpha component of the sampled reference phase vector. So, Vs is equal to V alpha. So, substituting this one, this will be equal to 3 by 2 Va sin pi by 3. Vs sin alpha is equal to the V beta component. That is a V beta. V beta is equal to root 3 by 2 into Vb minus Vc, that are our 3 phase amplitudes, corresponding 3 phase amplitude into cos pi by 3. Okay, if you substitute these values, finally it will come to Ts by Vdc Ts by Vdc into 3 by 2 Va minus 1 by 2 Vb after reducing this one, simplifying this one, minus 1 by 2 Vb plus 1 by 2 Vc, you will get this way. So, this again we can simplify is equal to Ts by Vdc. 3 by 2 Va I will put as Va plus 1 by 2 Va. Vd, this is Vdc. Okay. Va plus 1 by 2 Va one by 2 Va plus 1 by 2 Vc minus 1 by 2 Vb. So, this Vs is originally that sampled reference phase amplitude is generated with our values along the A, B and C axis, ABC axis. So, if you see here, finally it will be equal to Ts by Vdc into Va minus Vb. Okay. This we can further simplify. Let us see, we can write it like this. See, what I want you to know in this case is that T1 originally represented or written in terms of Vs and the cos alpha, alpha with respect to the sample reference phase amplitude in sector 1 is, now we are representing in terms of Va, Vb. So, if the 3 phase sample reference phase amplitude is available, sampling period is known, Vdc, DC link voltage is known, T1 is known. So, this again we can represent in a simplified way. Let us go to the next page. See here, now we can write it T1 is equal to Ts into Va by Vdc minus Ts into Vb minus Vdc. Vdc is unit is in volts, Vb is also in volts. So, for the DC link voltage, maximum DC link voltage, what is the instantaneous sampled Va, Vb, Vc? So, this become a fraction, it is a constant. So, Ts, this can be represented as Tas minus Tbs. So, what we are representing now, the sampled reference phase amplitude, we are representing in terms of a, in time, in seconds now, a fictitious time, that is proportional to Ts divided by Vdc. So, if VAS, VBS sampled reference phase amplitude at that instant is known, in sector 1 T1 is equal to that sampled value multiplied by TS by VDC for the A phase minus TBS, it will give you T1. So, this is very easy. Computation, there is not much computation like sin alpha, root 3 by 2, all those things are not there here. It is very easy, you can find out T1. Let us say what is T2 in sector 1. T2 is equal to 2 by root 3. Okay. Vs mod divided by Vdc into Ts into sin alpha. This we can write as 2 by root 3 into Ts by Vdc into Vs sin alpha is equal to V beta. That is equal 2 by root 3 into Ts by Vdc. What is V beta? V beta is equal to again root 3 by 2 Vb minus Vc. So, this root 3 by 2 and 2 by root 3 goes, this will be equal to Ts by Vdc into Vb minus Vc. This is in the fictitious time, we can write it TBS minus TCS. So, if you know the sampled reference phase amplitude in sector 1, at any position in sector 1, T1 is equal to Ts into Vm by Vdc minus Ts into Vb by Vdc or equal to Tas minus Tbs, and T2 is equal to Vb minus Vc multiplied by Ts by Vdc or Tbs minus Tcs. So, this is very simple, easily you can find out. So, in digital implementation, this is very fast. See, in sector 1, T1, T2 we have found out in terms of sampled reference phase amplitude. Is it possible to find out T2, T3, T4 also in other sectors also? Let us find out. Sector 2. So, let us draw our hexagon again once again for our reference. This is our space vector, voltage space vector domain from our inverter. It is a hexagon with the equal radii. Radii means amplitude of the hexagon. This is equal to VDC depending on the DC link voltage, this amplitude. So, again this is equal, this is sector 1, this is sector 2, sector 3, sector 4, sector 5, sector 6. Now, from the sector 1, our alpha has moved to sector 2 now, let us say. Now, let us say this is our new Vs. It is making a circle for uniform speed. See, previously it was in sector 1, we found out, now it is in sector 2. In sector 2, alpha has to be measured from the start of the sector, okay. But our V alpha is in this direction, V beta is in this direction. So, how do you represent this equation? That is T1 is equal to, we know T1 is equal to 2 by root 3 Vs mod divided by Vdc into sin pi by 3 minus alpha. This is general equation in any sector. T2 is equal to 2 by root 3 Vs by Vdc into Ts into sin alpha. Now, Vs sin alpha in sector 2, it will be along this direction, okay. Now, we have, and Vs sin beta will be perpendicular to this one. So, we have to find out the, now the alpha component along the start of the sector and perpendicular to in S2, what is the component along our alpha beta, where alpha is placed along this axis. So, if you see here sector 2, T1 is equal to 2 by root 3 Ts by Vdc into the component along this. Suppose the present V alpha V beta component, the component along this direction is equal to, that is along this direction, that is Vs cos alpha in sector 2. Vs cos alpha in sector 2 is equal to, we are taking in terms of our alpha beta component. That means from ABC to our 3-phase ABC to when alpha beta when convert, alpha is fixed along this axis, beta is fixed along this axis. So, the component along the start of sector 2, which will contribute both from alpha beta. So, that will be equal to, that is what we are talking about the Vs cos alpha type in the previous time, that is equal to V alpha cos pi by 3. This angle is pi by 3. So, this will contribute. How much V beta will contribute? V beta, this is pi by 3 means 60 degree, this will be 30 degree. So, V beta also will contribute towards that one, that is V beta into cos pi by 6. This is the new V alpha in sector 2. Vs alpha in sector 2. So, here Vs alpha means the component along in this direction, start of the sector. In terms of V alpha beta, this is the one, Vs alpha. Then, same the previous, if you expand this equation, then it will be, again this will be equal to, then what is the B beta component? B beta component in sector 2, Vs beta, that is Vs beta in sector 2. This is the Vs alpha in sector 2. Vs beta will be minus of V alpha, minus V alpha, then cos pi by 6, that is 30 degree, cos pi by 6 plus V beta cos pi by 3, that is V beta cos of this component into cos pi by 3. Okay. This is our final equation. So, what we did, the T1, T2 in any sector depend on the sample reference phase voltage Vs along the start of the sector and the perpendicular to that one, that is Vs alpha and Vs beta. But in sector 1, Vs alpha is equal to our alpha component, Vs beta is equal to beta component. Now, in every sector, the Vs alpha, Vs beta has to be transferred to our fixed alpha beta component by appropriately taking the component of this one, component of the Vs alpha and Vs beta. Now, here the Vs alpha in sector 2 and Vs alpha beta in sector 2, we have represented with the V alpha and V beta. Once we know V alpha beta is can be represented with our sample reference phase voltage. So, if you simplify this one, in sector 2, we will get a relation. We can simplify this one. Finally, T1 will be equal to 2 by root 3 Ts by Vdc into root 3 by 2 Vb into 1 by 2 minus root 3 by 2 Vc 1 by 2 plus 3 by 2 Va root 3 by 2. This will be, but that is we are getting this step from here, substituting for V alpha and V beta, then reduce it, you will get this one, that is T1. That will be equal to 2 by root 3 into Vb by 2 minus Vc by 2 plus 3 by 2 Va is equal to Ts by Vdc Vb by 2 plus Va by 2 minus Vc by 2 plus Va. This will be finally equal to Ts by Vdc into Va minus Vc. That means equal to TAS minus TCS. That is our fictitious timing. Why fictitious means the Va, Vb, Vc amplitudes as it moves to different sector, it can go both positive and negative, because VA can go positive, negative. So, TAS, TCS can also go positive and negative. So, what we want only positive time to find out the switching instance. We will come that one now. Now, what we are doing, the sampled reference phase amplitude from our T1, T2 equation, using the sampled reference phase amplitude, T1, T2 we are converting to a fictitious time. That time is proportional to the sampled reference phase amplitude multiplied by our fixed sampling period divided by VDC. So, TAS by TCS. In a similar way, we can substitute for T2 also. If you substitute for T2, it will be, I am writing, you can simplify that one. T2 will be in sector 2, T2 in sector 2 will be equal to TBS minus TAS, it will come like this. So, this way in all sectors we can find out what is the sample reference phase amplitude, gives how from the sample reference phase amplitude, how we can convert, how we can find out T1, T2 based on our fictitious time multiplied by TS by VDC. So, if you derive that one, the final chart will be, let us draw the table. This table can be used. This is the sector information, then T0 by 2, then T1 and T2. So, this is the sector, T0 by 2. Once the T1, T2 is found out, T0 is equal to TS minus T1 plus T2. Okay. From there, we can find out T0. Why T0 by 2 is required? We are splitting the T0 by 2 start and end with equal duration, and the active vector is placed at the middle. So, T1 and T2. So, the T1, this table gives the sampled reference phase, the T1, T2, T1 and T2 in terms of sampled reference phase amplitude. Let us say we will divide this one into 6 sectors are there, 1, 2, 3, 4, 5 and 6. So, let us in sector 1, T1 is equal to TAS minus TBS. T2 is equal to TBS minus TCS. In sector 2 is equal to see what is the T0 by 2, whether we have to do this one or is there any way, a simple way to find out, that will come later. So, TAS minus TBS, TBS minus TCS. Then this is equal to TAS minus TCS, T1, TBS minus TCS, here TBS minus TAS, then TCS minus TAS, here also TCS minus TBS, T1. Okay. Here it will be equal to TBS minus TAS, then TCS minus TAS, here also TCS minus TBS, TAS minus TBS, TAS minus TCS. Okay. 2, 3, 4, 5, 6. What is the advantage now? If the sampled reference phase amplitude, that is our VA, VB, VC is known. Multiplied each one with TS by VDC, you will get corresponding the fictitious timing in each sector, and symbol subtraction, you will get the T1, T2 in each sector. So, this is very easy to find out. Let us say what is the meaning of this one. Let us find out TAS minus sample reference phase angle and how to do the thing. Let us go to the next sector. If you see here, let us draw our reference phase amplitude. Let us say this is our A phase. This is our 0 line. Now, our B phase will go with a different color. Then let us have our C phase. Okay. As the speed varies, we want to generate different circle with the different radii. So, with the different radii, we have different amplitudes of the sine waves. So, the maximum inscribed circle happens, let us see, at this point, when the amplitude reaches here, +1 and -1. Okay. This is the one. Okay. So, +1 and -1. That time this sine amplitude reaches maximum, the circle, inscribed circle will have the maximum radii. Now, this ABC is for a particular circle with an reference with a radii equal to Vs. Now, let us take in sector 1. In sector 1, this is in sector 1. We are sampling the VA, VB, VC at one point. See, sector 1, the sampling will be somewhere here. This here we are sampling. When we sample, these are the amplitude. For the C phase it is here, B phase it is here, A phase it is here. When you sample it, and let us take, if you take the minus point to this point, let us say for a triangle waveform, as it moves from here to here, high frequency sine wave, high frequency triangle wave, as it moves from here to here, till this point, sine is greater than the triangle for A phase. So, you will get high signal here, after that it will be 0. Okay. Now, if you see here the amplitude till that point, it will be here. This is the amplitude, A phase. Now, B phase where it will be, that is here, amplitude if you take. B phase it will be here. The sampled amplitude is here. If you measure from the bottom side. But the sampled amplitude, if you see here, this is the amplitude. Always we start from the 0. The sampled amplitude for the A phase will be from here to here. For the C phase, if you take, this is the amplitude. Okay. Now, if you see here, as we go from here to here, if you say the sine triangle period, till this portion, till C is switched, what is the output? Sine is greater than the triangle. So, till this period, till this period it will be minus minus minus. Okay. So, the amplitude if you measure, we will get only the positive amplitude from here to here. Here you will get the B negative amplitude, C you will get this one, this is the amplitude you will get. This is for the B. But if you compare with the sine triangle, till this period, as the triangle waveform increase, we are sampling from here. So, as it moves from here, sine is greater than the triangle. So, till this period it will be plus plus plus. Okay. After that, this will go negative. So, this will be, C phase will be from here to here, plus plus minus. Then from here to here, it will be plus minus minus. Then from, if we extend this one, then from here to here it is minus minus minus. Now, we want to know the effective period. Effective period is from here to here. Effective period is, see, this is the 0 period, start of this is. So, effective period is only this much, that is active vector period, that is called T effective. Okay. Now, this is the T0 by 2, first T0 by 2, this is the last T0 by 2. So, we have to equally divide and place it. So, how do you find out the T effective period? Okay. You sample, first you sample the VA, VB, VC, VA, VB, VC, sample. Then convert it to TAS, sorry, TBS and TCS. How? That is VA multiplied by TS by VDC, VB multiplied by TS by VDC, similarly. Now, if you see here, the T effective period is between the maximum of the sampled value and minimum of the sampled value. See, minimum here it is negative, maximum is positive. So, you find out T maximum. T maximum is equal to maximum of our TAS, TBS and TCS. Then you find out T minimum, that is minimum of TAS, TBS, TCS. Okay. Then what is the T effective in sector 1? T effective is equal to T maximum minus T minimum. Okay. T effective we have found out. Now, how we will find out the T0? Very easy. T0 is equal to TS minus T effective. Okay. Now, we want the time period in positive, that is during which we have to see, if you see here, from here to here for the leg, if you say take the inverter, if you take the inverter like this, A, B, C, this is our VDC. So, for the A phase, let us say this is A, this is B, this is C. So, till this portion, till this period, we want the top switch is on. But if you see here, we are starting from here. A phase is only this much period is negative. So, what we want, shift the whole thing to the positive side. So, how do you do it? First, find out the T effective. T effective, and we also know the T minimum. T effective to on to the positive side, everything T effective minus T minimum will be always negative. Okay. The T effective minus T minimum, Ts minus T effective minus T minimum will shift the whole thing to this positive side. Okay. Then again you add T0 by 2. So, the offset to be added, so that everything go to the positive side is equal to T offset is equal to T0 by 2 minus T minimum. So, you have got the TAS, TBS, TCS, TAS, TBS, TCS. This depend on the sample reference space, sample it can be positive or negative. So, everything you want to shift to the positive side, and the zeros we want to shift it to the start and end with this T0 by 2. You add to this TAS, TBS, TCS an offset. Okay. So, we will write it here, add an offset of T0 by 2 minus T minimum. T minimum will be always negative. So, minus of minus it will be positive, to add to the TAS, TBS and TCS. What you will get the corresponding gate signal for the top switch in a sampling period. So, rest of the period bottom switch you have to turn on. So, this is the algorithm we want. So, let us go to the sector 2 now, how it works. So, let us find out the sampling instance for the T0 by 2 period. So, this is our 0 line, this is our A phase, this is our B phase, this is our C phase, that is A, B, C. Now, we are sampling. So, this is our maximum limit, maximum positive limit for the Vs with the maximum radii inscribed the hexagon or the maximum modulation index. So, here if you see here for the sector 2, we are sampling at this point. Okay. So, when you sample at this point, VB has the maximum amplitude at this point. This is VB. Now, let us say the sampling, we are sampling at this point, and VB has the amplitude here. This is VB. Now, VC has the amplitude here, negative. So, this is what is this one is for VA. So, here the maximum amplitude is for VB and the minimum is for VC. So, if you see here till this point for a sine triangle, till this point A phase top switch is on, B phase top switch is on till this point from here if you take, that is from here, starting from here. A phase is from here to here, and C phase it is here. We are sampling it here. So, C phase will have here up to this point. Okay. Now, which if you see here, this is our maximum range here. The T effective is always T maximum and T minimum, that is this one from here to here. This is the T effective period. If you see here till this point it is plus plus plus, then till this point it is C is negative, so plus, plus, negative. Then from here onwards up to this point, this is B phase is, so it is minus, plus, minus. Then from here to here it is minus, minus, minus. This is in sector 2. If you see here, this is 7 plus, plus, minus is equal to vector location 2. This is 3, then this is the 8, 0, okay, in our space vector diagram. So here also the same we can use it. TAS, TBS, we can find out TAS, TBS, TCS, we can find out. Then T effective is equal to T maximum and T minimum. T maximum minimum of this phase, then T offset is equal to T0 by 2 minus T minimum. This offset you add to this one, everything will go to the positive side, and we will get the corresponding gate signal for the top switches of any leg, and the remaining period in a sampling period we have to switch on the bottom switch. So this algorithm will be very simple. So let us write down the algorithm for digital implementation. Yes, very simple algorithm. So our algorithm for the space vector PWM, we will write now. First we will get from the control V alpha and V beta. From there we can find out VAS. V alpha is equal to 3 by 2 VA, and V beta is equal to 3 by 2 VB minus VC. Also we know for space vector VA plus VB plus VC has to be 0. Okay. Now VA, VB, VC is not gone, then we will find out TAS is equal to TS into the sampled value of VA divided by VDC. Similarly, TBS is also equal to TS into VB by VDC, and TCS is equal to TS into VC divided by VDC. Okay. TAS equal to TS into VA by VDC. TBS also is equal to TS into VB by VDC. TSC is equal to TS into VC by VDC. Then we have to find out the maximum and minimum. That we will use a 3 element sorting algorithm. Okay. Let us take T maximum is equal to TAS, T minimum also we will take as TAS. Okay. Now, if TBS greater than T maximum, then T maximum is equal to TBS. If TBS less than T minimum, then T minimum is equal to TBS. Then one more. If TCS greater than T maximum, then T maximum is equal to TCS. Or if TCS less than T minimum, then T minimum is equal to TCS. So, by this sorting algorithm we can find out end of this command we can find out which is maximum, which is minimum and which is the middle one. Now we can find out the effective time calculation. The effective time calculation that is T effective. This is very easy, is equal to T maximum minus T minimum. From the previous sorting algorithm, we have find out what is T maximum and what is T minimum. T effective we find out. Now T0 is equal to T sample minus T effective. Now we want to offset, because all this till now period our TAS, TBS, TCS will have maximum value and one will be minimum value. Minimum depending on the sector it will have minimum or maximum. Now for the gate signal we have to get the positive value. So we have to add the offset. The T offset to be added to all the TAS, T offset is equal to T0 by 2 minus T minimum. Okay. Now our gate signals, that means the gate in a sampling period, gating signals during which the top switch in a leg is turned on. Okay. This is equal to adding the offset. So TGA will be TAS plus T offset. TGB is equal to TBS plus T offset. TGC is equal to TCSS plus T offset. Okay. So rest of the period in a sampling period, the corresponding bottom switch you turn on. So this algorithm is very simple. The advantages of this algorithm. Of the PWM algorithm. No lookup table is needed. Sector identification is not required. Is not needed. The angle alpha with which the reference space vector makes with the start of the sector, the alpha angle information is not needed. Okay. Voltage space vector amplitude. Measurement is not required. Not needed. Then what is needed? If you see here, we require only the sampled reference phase amplitude. in a sampling period are needed. So, it is very easy. It is a simple sorting algorithm. There is no multiplication, there is no square rooting, there is no sine and cosine function is needed. So, we can easily from the controller, if you know alpha beta, we can easily find out transform in the alpha beta into ABC. Then once you fix the TS for a particular inverter switching, let us say 1 kilohertz 1 kilohertz sampling, it will be 1 millisecond. But if you see here in a sector, this is our hexagon. Let us say S1, it is go from 100 to 110, then 111, 000. So, in a sampling period, we will start from 000 if we start, next it will go to 100, then we will go to 110, then the start T0 by end to T0 by 2 will be 111 T0 by 2. This is one sampling period. In the next sampling period, we will start with 111. So, that will ensure minimum switching. Then we will go to 110, then 100, then 000. So, if you see here, this is the next sampling period. So, inverter started with a 00 state and ended with 00 within 2 sampling intervals. That means, in 2 TS, inverter has come to original state. So, inverter switching period is equal to 2 times the TS. So, for a 1 kilohertz sampling period is required. So, our TS has to be 500 microsecond. Then appropriately, we have to toggle a counter for the 0 and positive and switch between the sequence has to be changed. So, this way very easily we can implement the space vector PWM in the linear modulation. Okay. In the OR modulation, that means when we want to go to extra modulation range, there the 0 period will not be there, 0 period will be 0. So, correspondingly whenever the 0 period become negative, we correspondingly adjust the gain such that T1 plus T2 is equal to Ts. Then you get the OR modulation. Now, with this basic introduction of front end AC DC to AC converters, now we will use this one for a motor control for a typical induction motor drive applications. We will study this one in the next class.